Okay, so here we have a firecracker which explodes, and the initial mass of the firecracker before exploding is given to us to be 100 kilograms, and the initial velocity was at rest. So before exploding, the firecracker is just sitting there, and M1 and so it explodes into three parts, right? So with masses m1, m2, and m3 given as follows, and m1 has velocity 75 meters per second going in the positive x direction, m2 has a velocity of 52 meters per second going in the positive y direction, while m3, our target, has a mass of 0.041 kilograms, but we don't know the velocity, meaning the speed and direction. We don't know, and that is our target. So let's start off with the diagram as usual. First of all, denote our axes to be plus x in this direction, plus y in that direction, and then let's draw our situation out. Okay, so M1 was going in the positive x-axis, so let's maintain color. M1 was going in this direction, 75 meters per second, and remember, like, this is our initial situation, so initially all of them were at rest, and so let's just call them V1F in the positive x direction. And then we have M2 going in the positive y direction, M2 going this way, V2F is 52 meters per second, and we don't know in which direction M3 is going, so that is our target. So let's say M3 is a part that is going in this direction, alright, and we don't know what direction this is, so we don't know what this angle is as well. Let's call it theta. So this is our very simple diagram. When with our chosen axis, we see that let's also not forget to denote this vector as V3 final, and since V3 final is not aligned with our chosen axes, it will have components along x. Let's call this V3 final x and V3 final y. Alright, now our goal, remember, is to find the total velocity, both magnitude, that is the speed, and direction. So how would we go about doing that? Well, we know that in an explosion, external forces can be ignored. So we will have momentum conservation, that is, let's again be mindful of our colors. Momentum conservation means the initial momentum of the system will be equal to the final momentum of the system. Now, initially the system was at rest, and remember that momentum is nothing but P equals mass times velocity. Since initially the velocity was 0, the momentum was 0. So initially momentum Pi is 0. Since momentum initial was 0, that means momentum final would be 0. And this principle of conservation of momentum must be satisfied in the x and y directions. Alright, so it must be satisfied in both directions independently. So that means we can say that since total Pi was 0, Pix was also 0, and that should equal to Pfx, and these are both vectors. Similarly, Piy was 0, so Pfy would also be 0. So that is our starting principle. Now let's go ahead and solve this problem using this. Alright, so in the x direction, what do we have in the final momentum? P final x equal to P1 final in the x direction plus P2 final in the x direction plus P3 final in the x direction. We know so far that total final momentum in the x direction is 0. And what is the P1 final x? P1 final x is just m1 times v1 final, which is completely in the x direction. That is 75. So m1 is 0.25, sorry, times 75 meters per second. Then what is P2 final in the x direction? Well, V2 was completely in the y direction, so it didn't have any velocity component in the x direction, so it doesn't have any x component of momentum. So P2 final x is 0. What is P3 final x? We know that we have denoted the x component of V3F to be V3Fx. So the momentum due to the x component of the third part in the in the final situation is just mass 0.041 times V3 final x. Alright. Then we have an equation. Just take 0.025 times 75 on one side, and then we have something left here. Well, we have missed the fact that there should be a negative sign because V3 final x is in the negative x direction. So this is a negative 0.041 times V3 final x. You can divide out the negatives. If you want to find V3Fx, divide both sides by 0.041 so that these go away. And on this side you have divided by 0.041. This leads us to a final velocity for the third part in the x direction to be, the speed is negative 45.7 meters per second. So this is the x component of the final velocity of the third part. So 1/2 of the problem is done. Then we have to contend with the second part, which is to find the y components or the y contributions of momentum. So in the final y direction, we have Pfy equal to P1 Fy plus P2 Fy plus P3 Fy. So the summation of all the y components of all the separate three parts is equal to 0 because the final momentum in each of these x and y directions must be 0 to conserve momentum. Like before, what is the momentum of the y component of momentum of the first part? The first part had velocity only in the x direction, so the momentum in the y direction for that is also 0, plus V2F was a completely y velocity, so the momentum would be the mass of part 2, which is 0.034 times the velocity in the positive y direction, which is 52. And what is P3Fy? Well, we have denoted the y component of velocity of the third part to be V3Fy. So this is just the mass 0.041 times, remember that this is also in the negative y direction, so negative V3Fy. Solve this like before. Take 0.034 times 52 on one side. On the other side we have left minus 0.041 times V3Fy. Divide both sides by negative 0.041 so that these go away, and on this side you have negative 0.041 dividing this number right here. From here we get the y component of the third part of the velocity to be negative 43.1 meters per second. That is what we started to look for, right? Then we are not done yet because we have only found the x and y components. We want the total velocity of the third part of the firecracker. So the x component of velocity was negative 45.7. The y component was negative 43.1. Then the total is just this part right here, the hypotenuse of this triangle, directed less so in making an angle theta. So this is our velocity triangle, and this is V3 final. You can find the magnitude of V3 final, the total speed of the third part of the firecracker after explosion, by using Pythagoras theorem as before. V3 final x squared plus V3 final y squared. You take the whole square root of that and end up with a speed of 62.8 meters per second. And to find direction, again use tangent. Theta equal 43.1 over 45.7, and take the tan inverse of this to get theta as 43.3 degrees below the x-axis. Alright, so this is what we set out to look for, and we have successfully found the final velocity of the third part of the explosion by using conservation of momentum. Alright.